So today we will step into chapter 4. I don't want to rush the progress in our class, but I believe we will end before the 10th week. But we will have a midterm. Midterm is a written exam, and you will apply the MATLAB to help you. But this chapter will be the, I would say, appendix, 附件, but it's worth to understand. It's quite complicated because I use this kind of knowledge for our research. So you may see it's not normal application you may use. Maybe later on, if you step into the robotics field, then you will need. But at this point, you just realize a little bit will be fine. So I would say, yeah, it's good to know, and hope you can enjoy that later on. Okay. So the velocity kinematics. Okay, kinematics include several physics parameters. Kinematics is different from dynamics, because kinematics did not involve with force. So when I say kinematics, you need to realize right away, it considers about the position or rotation angle. It considers about the velocity. Later on, we will introduce that velocity. Okay. Of course, we have an angular velocity or linear velocity. Okay. Then we consider about the acceleration. But for the Newton's law, so over here we will introduce a new item. Okay, the new item. Of course, it invented by this guy called Jacobian. Jacobi, it should be Jacobi. He is a mathematician, I think. Okay. So I divide the textbook into several logical segments. Then it will be easier for me to introduce to you. Okay. So in the previous chapter, okay, we have the forward kinematics ready, because I already introduced the major point, and we have the joint position to the end-effector. But to the end-effector, including the orientation and the position. So we have actually we kind of have everything, end position and orientation. And as I mentioned, maybe jump to the conclusion later. Okay, let's go through the whole part. Okay, so we derive a velocity relationship related to linear and angular velocity for any vector, because our final matrix. We just finished the review for chapter 3. So we have R11, R21, R31, and O1, O2, O3, something like that. Okay. So our matrix is elegant because the final transformation matrix include rotation section for any vector, which is this part. Okay, rotation, and also the linear position. I should not put linear. Yeah, it's confused. Maybe position. It's fine. It's fine. Okay. And we don't have any physical parameter related to velocity. And that is what we want to discuss in this chapter, okay? And so over here, okay, he mentioned mathematically the forward kinematics equation defined the configuration space of joint position to the space of Cartesian position and the orientation. What he tried to say is the forward kinematics include a lot of information. However, in space, we know it's complicated. As I mentioned, in space, we have a 6 degrees of freedom, including the linear XYZ and rotation XYZ. Yes, so it mentioned exactly the same thing. But how about the velocity relationship? Can you describe from the previous final transformation matrix? Oh, this is a question, okay? So it cannot. So we need to step into the Jacobian concept to demonstrate how can we connect this relationship together, okay? So eventually, Jacobian is a matrix generalize the notion of the ordinary derivation of a scalar function, and it did not mention too much useful information here. Eventually, the Jacobian can do that. We have a final transformation, but what is the relationship to the velocity? Okay. So before we step more deeper, and we can define what is the Jacobian can use for, okay? Eventually, it can use for planning and execution smooth trajectory. Smooth trajectory is quite important. I want to tell you a story. This is the online meeting this week, and we have a project is going. We just follow online discussion every month. And we try to develop the very complicated robotic system. But for the robotic system, it's easy for robot arm. We already solve any kind of problem related to robot arm. Position, angle, orientation, force control is okay. But how about the finger? If I have a 2 finger, that's a normal standard equivalent to the robot right now. But if I have 5 like a human, how can I control the finger position? And position is only the issue. Can you look it back? We need to consider about the velocity. Why we need a velocity? As I mentioned the application before, if you need to grind something, if you use the position rule, maybe yeah, it can work. But if you can design a velocity trajectory, then will be work as smooth as you can expect. Like a human being, human arm, human brain, we can always control our hand. Normally, we can control our hand smoothly. If you want high velocity, slam. If you want a slow velocity, maybe touch a dog, then you can do it as well. We will try to do that on the ice cold machine, okay? So first is how can we planning and the execution the smooth trajectory. Execution is 执行, okay? And also, okay, there's another important part, but I will not go to the part today. It's the singular configuration. In some posture, 姿态, for the robot, you will become singularity. So to solve this issue, we have a lot of technique to do that in the programming. But in some mechanical design, it is unavoidable. So for the Jacobian, it can help. Okay. And others, I just leave you to read through. I think, okay. And some we can derive the dynamic equation. Actually, we use the Jacobian for our research. It's for dynamic, I would say, the dynamic research. Okay, it's very useful. And that's the first time I actually try to apply it on the real machine. So I would say, yeah, it's useful, and we really appreciate the kind of concept, okay? and the others we can transform the force and torque, any other stuff. So this is the utility for the Jacobian section. Okay. And over here, I will have an in-class activity. Before I design a lot of in-class activity for you guys, say, oh, how can you realize what's going on over here? Okay. So first, I would like to ask you to draw the concept about the description below. Yeah. When a rigid body moves in a pure rotation about a fixed axis, every point of a body moves in a circle. The contents of this circle lie on the axis of rotation as the body rotates. A perpendicular from any point of the body to the axis sweep out an angle, and this angle is the same for every point of the body. According to my description, this is a description I wrote before. So what would it like if you draw on the paper? What did I say? What did I say? Okay. 这是现在的作业，来，公瑾帮我按暂停一下，先按停好了。So there's two purposes for this test. One is understand what did it describe here. At this point, I see few people. Yeah, few people can understand exactly what's going on. For the everything I have in mind is I just want to describe an object, or we call rigid body in our old class, because we always taught about the rigid body. But what is a rigid body? Later on, I will define it. So when a rigid body rotates in space along with the z-axis, that's what happened. That's what happened. So it will rotate to somewhere, okay? And somewhere they have an angle with theta, or with a theta. So it's easier, we say, okay, the angle is the same for every point of the body. So if the body, yeah, you don't need to change your stuff. Yeah, I just want to see what's going on, and I already see. Okay. I want to show you it's a rigid body, but it's a huge rigid body. So when I describe, oh, it rotates along with the z-axis as a theta, okay, I can describe it. Can I? Maybe I cannot, because large rigid body have a different section, have a different point. They have its length. Okay, so over here it did not come out the correct representation, because we only have the rotating angle. But how about the point at the rigid body? I did not put a point over there. Other point except the center of mass. Sometimes we need this information. For example, this is my end-effector. Of course, I have the angular velocity for the end-effector. But what about the finger velocity? Can you describe it as angular velocity? Yes. But how about I need not only angular velocity? For example, if I want to touch this screen with proper velocity, so I'm looking for the linear velocity. Then at this point, it is not enough information for me to compute the linear velocity at this point. Okay, so I would say the Jacobian is trying to connect this relationship between the rotation velocity, or called angular velocity, to linear velocity. Okay, so this is exactly what I'm trying to image. What is the description in the previous slide? Okay, and yeah, what's going on over here? So in fact, computation of velocity v is normal to the goal. They can involve with like a dynamic close, but we don't need to go to the step, and we just try to describe the angular velocity will induce or induce the linear velocity in a rigid body. So what we interested is to describe the motion of a moving frame and the motion of the origin of the frame through the space, and also the rotation motion of the frame's axis. So eventually, if our frame can rotate, for example, I can rotate it in the k-axis. Normally we put the k-axis as a z-axis. Then the rotating speed is theta dot. Okay, theta dot is the velocity, angular velocity. Okay, so for the linear velocity, we need to compute according to their radius. Okay, so there's a normal concept for that. This is an easy part because you can show in a lot of dynamic book in the chapter, the first several chapter. Okay. I put more detail because when I read through the whole textbook, yeah, it describes a lot. Okay. So why we need a Jacobian? In the previous chapter, in order to specify the orientation and rigid body object. Oh, okay. Practice to summarize. Okay, I mark as I want. Okay. So, if I read through the whole part, that's not interesting, right? Okay, I will let you guys read some part of them and summarize for us. Okay, so maybe take another 5 to read through the whole part, and we need a volunteer. Yeah, we need a volunteer to increase your participation score. Okay, what is summarize? What is summarize? Summarize 是看完之后用简单的一句话告诉我他在讲什么，叫 summarize. So I say practice to summarize. This is very important for your language practice. I say language including the Chinese language. Not only you can speak Chinese, it's okay. Experience the same angular velocity. Yeah, in a rigid body. In a rigid body. But what if I need the different spot? When I say spot, it's a different region of the rigid body. Individual velocity. Then at this point, I need a linear velocity. As I mentioned, the whole end-effector swept in a very high speed with the angular velocity. But how about the fingertip or the palm center? If I needed the velocity, then it is not quite full information for that. So that's why I'm saying they are described over here is we need the linear velocity corresponding to the angular velocity 1. Okay, so this is the part, and I would say the summarize for this session. Okay, and also of course, when you specify angular displacement, it is a planar problem. Okay, planar problem. It's planar problem in the case. And yeah, for the first one, I did not highlight anything, so it's nothing. So therefore, to use the theta dot to represent the angular velocity. But we already have seen in chapter 2, the choice does not generalize to 3-dimensional case. Either when the axis is rotating is not fixed, because the angular velocity. Okay, it mentioned the summarize over here. Let me summarize for you. Okay, The summary over here is they try to describe why the angular velocity is not enough information because it cannot, because we multiply several matrices together to find a final matrix, transformation matrix for one joint. But this one joint for the angular velocity is not the only one angular angle to produce because it multiply at least the two rotation matrices together, right? No matter you multiply 0 or non-zero term. So it's a compound result. At this point, if you want to control the speed, I don't know which angle I should control. There are two. So how can I control the final compound angle velocity? 来，讲成中文我听听看。中文啊，就是说，今天 angular velocity 不好用。我今天如果要做 control， 这里就是 for control section。我要做 control， 我要控制这个的转的速度。我要控制哪一个角啊？不知道。为什么不知道？因为 one joint is computed by at least two angular velocity, right? Maybe we have a rotating by z, right? So theta rotating by x. So it's alpha, beta, I forgot. Okay, it's maybe beta. We have a two compound angular velocity multiplied together. So you don't know which angle velocity you need to control to produce the final one. So this is the true reason. If I want to control my robot's speed, then if I observe from the angular velocity point, or I would say term, then it is a little bit difficult to control it. As he mentioned over here, is the result of multiple rotations about a distinct axis. Got it? Okay. So it's quite I spent some time to understand what's going on. Okay, I hope you can receive more information from my explanation. Okay. So for this reason, we need a more general representation. When I say more general, it means what is the general coordinate? Yeah, we did not mention this term before, so it's not a good question for you. But when we say general coordinate, it means this is the coordinate we can represent at least 1 degree of freedom movement. If they can represent at least more than one, that is not a general coordinate. Okay, so this is a concept I just think about and share with you. Because XYZ is all orthogonal, right? So there is no substitute for x-axis. If you want to rotate in axis, y and z cannot help. So this 3 must be general coordinate. Okay, so we need a more general representation like this way. Oh, if we don't have this kind of way, then the angular velocity have the issue is they couple together. So it's not good one for the general representation. Okay, I just try to come out and share with you. Yeah. Okay, any question? Yeah, at this point, I know you guys don't read at home and don't focus on in the class. That's a little bit sad. Yeah, if you participate in this class but get nothing, yeah, it's a pity. You waste the time. Okay, so I would suggest you to read something. If you don't do that, yeah, it's your life. Okay. So rotational velocity, linear velocity, we will differentiate in this chapter. And describe an end-effect is nonsense to use the, okay, this is my summarize. Okay. The textbook is complicated. I would say why I spend a lot of time on that. And you can see the result I put into the PowerPoint is summarized or is organized in my way. Okay. For example, when you start to read this chapter, and if you follow the sequence, you will get boring, very boring. But every mathematics book, I would say they all do it by this way. For example, we need a skew-symmetric matrix. So they put a skew-symmetric matrix in the front. Then later on, I don't have interest in it at all. Yeah, I can feel the way. But as an engineer, I'm not sure engineer, okay. As a scholar like us, we need to explore the theory and try to apply the theory in a practical way. Then we need to go into more detail for the mathematical part. In that case, we need this session. Over here, I just want to briefly introduce a little bit. If you have interest, you can explore whatever you have in your PDF file, okay, and you will have a lot of fun. I will not guarantee that. Yeah, it depends. Okay. For the skew-symmetric, I would say it describes a lot, but the easy way is I show you the matrix form. It's easier. So skew-metric is skew-symmetric. Okay, it is along with the orthogonal. You know the orthogonal, right? You must know the orthogonal. Orthogonal is the I would say the element in the middle of the skew line. Okay, so along the skew line or along the orthogonal element, there are elements in two sides. Okay, so for example, the x3 and the other negative s3, they are the same, although they have a different sign, but should be okay. And the other along with the orthogonal part is S2 and S2 minus S2 and S1 and minus S1. This matrix is called skew-symmetric matrix. So in some matrix computation, we need a spatial matrix to help us to really to do the computation, not to understand. You don't know, you will not understand, but it will help you to do the computation. Okay. So at this point, we need to apply the spatial characteristic for this matrix. So we need to apply this type of matrix. For example, we need a S transpose plus the original one equal to 0. We need this characteristic, and we also need the ij. The ij will be different. I would say, yeah, it's different. Okay, and the plus together will be equal to 0. This is the second one. I don't want to go to more detail, but I just want to show you. What is the transpose? Just prevent you forgot everything. So I have an example here. So when a transpose is, you have an element 1, 2, 3, 4, and you put the row element to the column element, then it's become the transpose. So if you have a 2 by 2 or 2 by 3, then it will become a little bit different. But when we use the symmetric, it means we have at least like a 3 by 3 or 4 by 4 matrix. There will not be this kind of non-symmetric one. Okay, so over here we always have a 3 by 3 matrix, so it's symmetric. Okay. Then over here we put the vector ax, ay, az in the matrix A, and we do some calculation. So the first example is if we try to represent the unit vector ijk into the skew-symmetric matrix S, then they will become by this way. Okay, why? Okay, the first thing you need to know why. Because when I equal 1, 0, 0, the element over here will exist is AX. Same situation for the J is AY, K equal to AZ. So when you put everything together into the skew-symmetric matrix, the final S matrix become by this way. Okay, so it did not mean anything. It just let you know, okay, how did it operate in the skew matrix 1, and yeah, so it's an easy one. Okay, so right now you have a new knowledge today is what is a skew matrix, and some kind of two characteristic for that. For this part is more detailed and more complicated. So I will just leave over here, and if you have interest in, you can take a look. But eventually, it just told you it's linear, so you can do the superposition. So superposition means the linear system always can do the superposition. They do another, say, adding together. They say superposition. So there's an alpha in between. Then they can have this kind of characteristic for their results. Okay, I don't want to go too detail. And there are some proving. Okay, and proving process is not the interesting part for me. But we already know what's going on, so I don't want to bother you guys. I want to go to the very final one. Okay, this one is more important than that. Okay, so the derivation of a rotation matrix will become by this way, because we already know it's orthogonal for all follows. The textbook is weird. Sometimes you call it skew matrix. Sometimes the R, they say, oh, the R is orthogonal matrix. Okay, so you cannot blame what they want to say, because in textbook they try to collect a lot of fundamental knowledge for you, especially for if you do the matrix computation, you need a lot of background knowledge. The property of the orthogonal matrix itself, if the matrix and itself multiplied by the transpose the matrix together, then you will become I matrix. Okay, so if you differentiating on both sides, then you will equal to this part. I think this is easy calculus for you. And for the I matrix, because it is, what is it? It's equal to 0 because it's numerical, right? Because it's 1, okay. And over here, we define the previous defined skew matrix S equal to this term. Okay, and skip the last one. I think the better one is this one. We prefer this one. The previous this one. Yeah. 哦 ，OK， 也可以。This one to this one. Okay, we prefer this one. So over here we have the rotation matrix R and differentiated by theta. Okay, so eventually I have the rotation velocity. Okay, and I have the S skew matrix and the original rotation matrix. We needed this relationship to continue our derivation. Okay, so over here I mentioned equation 415 is very important. It computes the derivation of a rotation matrix R is equivalent to a matrix multiplication by a skew matrix. So that's the point. We use the skew matrix over here. And the most common in content situation is the case where R is a basic rotation matrix or product of a basic rotation matrix. Anyway, R is a rotation matrix, and we can build up this relationship. Later on, we will apply it a lot. We will apply it a lot for the equation 415. So for the whole explanation is help us to obtain this final one, and this final one can help us to do something. Okay. No matter how many questions we explained, I think the best way is to practice. So we apply the rotation matrix along with x-axis. So the original x-axis, you can come back the memory. Don't do that. And you can look back to the chapter 2. It's I believe it's this one. Negative. Eh, 这可以写哦。这个写的不好。Okay, so if you want to rotate along with x-axis, then the rotation matrix is something like this. Okay, so you can see over here, if you differentiate with theta for the first one, then they will become the first matrix. And if you transpose for your r-axis, then will become the second matrix. You multiply together, then you obtain the S matrix. And follow the rule, say skew-symmetric matrix. So we prove this is correct. This is correct for now. And follow with the result, we can also define if I have an x rotated with rotation axis, rotation y, and rotation z, we all come out the same result and build up the relationship for our preliminary preparation for the derivation. Okay, so this is the part. Interesting, huh? Okay. So the same question for 15, they can also revise to this one. So we have a general case over here. So if I have a rotation, my axis will rotate, then I can build up the relationship with skew matrix multiplied by my original one. Okay, and later on they will show a case. This case is over here. It makes sense, right? It needs to make sense to you because it is in chapter 2. If you want to move a position vector observe from the other coordinate, the formal way is by this way. Okay. Can anyone tell me why is the R1 represented 2? What is the meaning for R10? I always read R10. There's a meaning for that. referring the joint 1 to joint 0 will be easier to say. But joint 0 is our global coordinate. 0 always be our global coordinate we define in this textbook. Okay, that's good. So with this kind of representation, yeah, you will need, okay, in the exam, you will understand what's going on for this computation, because you try to move one position vector, they already observe in coordinate 1 or joint 1. So it's not the absolute coordinate we want. We want to, what is the absolute coordinate? Is the coordinate we want to observe from the coordinate 0. So this is the rotation matrix. We want to rotate it back to coordinate 0. Okay? Okay. So over here they have a computation for this one. Okay, and include the angular velocity. Okay, it's quite complicated, but should be easy to understand if I write it by this way. Okay. Over here, it mentioned for the upper formula. If I want to have the linear velocity for P0, yeah, I already know P0. And I know how to convert to put P0. Okay, and although this position vector is in P1, so I differentiate with a time coordinate, time vector, time variable. Okay, so I can have the formula like we described before. So the rotation matrix will rotate, right? And follow with the formula we provided in before. And eventually you can have the final answer for omega not multiply. It's a product with the P0 because it's a product except the omega. Omega is a scale quantity. Okay. So what is omega stands for? Omega stands for the rotation for the R matrix. Yeah. In this case, I'm not sure in join 1. Should be join 1, right? Okay, join 1. So the join 1 will move, will rotate, right? And the rotation angular velocity is omega. So the final one is omega product the P0 is the final answer. So when you see the first and the final one, then you will see it is easier to understand. But what is the question and the answer in between is the derivation we just provided in the previous slide. Okay, so result is easy. You can easy to understand, but why it will cause this kind of result is the mathematics we built up before. Okay. So let me organize it a little bit again. Is if I want to know the position P0's velocity. It's called linear velocity. It's at 1 point, right? Then when I perform the calculation and have the previous property in the previous slide, the final answer will become the omega product the position vector P0. It seems makes sense a lot, but the process is quite important because you will never know what kind of situation you will face. So you still need to understand what's going on over here. And I think the point is over here. Because we have this property in the front. If we don't, then it's almost impossible we come out final solution. Okay. So in this case, they try very hard to write several pages. They try to build up the relationship between the rotating axis with your rotating angular speed with your original rotation matrix. So this is the key part as it mentioned. Okay, I forgot it's 15 or something. This is a key part for that. Okay, and also I describe a little bit over here. Yeah, just for your reference. Okay, I suggest you have a better understand for this part. If your English is not as well as you expect, then at least you need to understand the equation and you know how to do the computation. That should be fine too, but I will suggest you both of them should practice more before you leave the university. Okay. Okay, for this session, for addition for angular velocity, I will leave it to you. Yeah, because I think we may not use too much for this part. And I want to step into the session 4.6, the derivation for Jacobian. I would say this is quite hard to understand when I first to involve in this area. Okay, so especially for the presentation in the textbook. So I will go through the part step by step. Then you guys, if you pay attention for that, it will help, yeah, for you to read through the textbook. If you don't, then you need to take at the same time like me, okay, to go through the whole part. Okay. For the derivation of the Jacobian, they always consider about many links. So we don't consider about a 1 degree of freedom. Yeah, it don't make any sense for this kind of complicated stuff. Okay, so many link, when you see T is the whole summation together. So we have a several joint, 2, 3, 6, and all multiply together, the A1, A2 until A6 together. Then the final one will become the Tn to 0, okay? And eventually we will have a very consistent 4x4 matrix. For the Rn part, describe about the rotation. For the On part, describe about the position. Remember, what is the dimension for this one?
3 dimension.
3 dimension. We call 3 by 3. Okay, no. It did not pay attention too much, huh? It's 4 by 4. It never changed. Not until, after chapter 2, every final transformation is 4 by 4. Why? Because the rotation matrix is 3 by 3, right? Position matrix, how about position matrix? Is what is the dimension for position? It's 3 by 1. So we need to add expand matrix to contain the whole information. So we have a 0 here and 1 over there. So if you expand everything, so what I say is that after chapter 2, the final transformation is always 4 by 4. The design is we can do the computation easily. So we contain the rotation matrix and the position matrix in one extend matrix form. Okay? So over here we have two information. It's the rotation matrix and the position matrix. And we also have a joint variable they call Qi. And when they say Qi, it means which joint it has. Okay, That's it. So the objective of this session is to relate to the linear and the angular velocity of the end-effector to the vector joint velocity qi dot. So the issue for the previous transformation Ti is we only need the variable q, but we don't have any idea for the q dot, which is the velocity. So over here, we try to build up this relationship through the Jacobian. Okay, through the Jacobian. Okay, over here we already, okay, no, actually we need to go through a little bit. What is ON0? Here, okay, because they use a sum, different one. ON0, position matrix Q, and they call it N0 dot as a V. No, 写错 should be dot over here. Dot here, not here, there. Okay. Okay. Let's represent it as a velocity here. And where's omega? My omega. Here is also a little bit confused, huh? Omega is here. Okay. Omega. It did not mention sum. Okay, should be here. So it's R dot, Rn dot. It did not say omega N0. Omega N0 equal to hold on a minute, huh? Yeah, it's very confused for this session, so I need to make sure. We know this part is omega. This one should be okay. Then I better roll it by this way. T. Okay. So at this point, let's divide it into two parts, and I want to roll it here. Linear velocity. Actually, it mentioned in the over here. And here is angular velocity. Okay. And why they want to do that? Because they want to build up the relationship by this way. The Q, of course, it stands for the joint, but the Q dot is the joint velocity, and it can adapt for the whole linear velocity and angular velocity. Let us see the arrangement for the matrix. So over here, we come out a final equation. The equation, why I say is a little bit confused, is because it included a new parameter. So that's the reason I think it's a little bit lousy. Huh? So it's Jacobian with Q dot, and it's JV, JW, and the Q dot. This is J. Because it don't look like a J, JW. Okay. We created a new parameter by its own velocity item. The difference is one of them is linear velocity. The other one is angular velocity. They represent it by this way. And they put the matrix in this term, okay? Is another description. But over here is kind of still a mess. But don't worry about it. I will explain a little bit later. Okay? But over here, you can realize we divide into linear and angular velocity over here. Here and here. Okay. I would say it's complicated because I pause. For one single joint, yeah, we have a linear velocity. Oh. And we have angular velocity. Okay. For the position, it's easy. Actually, not easy. Yeah. We still have a 4x4 matrix to describe it. But how about the velocity? We need a linear one and the angular one to describe it. Where is the linear velocity? Where can you imagine that? For a joint, yeah, say, oh, if I need the final the joint link with some link, right? And the link in their end, they have a linear velocity. Oh, okay, I can got it. But for the joint itself, it can rotate. So it belongs to rotational velocity. These two velocities, they all retreat and put into the Jacobian, do the calculation. So you can imagine that this is different one. This is different from the transformation. You cannot multiply other with others. You will get confused. So this is a totally new transformation matrix compared to the original chapter 2, chapter 3's the full transformation one. Okay, let's continue. Over here, they just mentioned, oh, okay, the I forgot the name for the Greek characters. It's sometimes called a body velocity, or the whole body. The body means the whole mechanical system, robot system, okay? And the velocity is not derived from the position variable because some of them is from the joint velocity and some of them is related to our location in the arm. So it's not exactly what we expect from the time derivative based. For example, we have a velocity x, we have the position x, then we have the velocity x dot and acceleration, something like that. What you try to explain is we are not come through the part. We are come through the very weird part. Yeah, the weird part is we try to differentiate into two categories. So that's why Jacobian is so special, because it's not a regular one. Okay, that's what I try to say. Okay, let's skip this one, and but we need, right? Later on. I want to go to the very complicated part. Okay. Okay, I think I better use this slide to continue what I want to describe. So the J equal to JV and J omega, and the JV is linear, and the J omega is another linear. So if I divide with something, it did not have any in characters. Let me take a look. No. Okay. It did not have this kind of representation, but I want to put here to help you to understand. Okay, so eventually the Jacobian have a 6.6 multiply n, okay, matrix. Because for each joint, they will provide the element to describe the joint linear velocity in xyz, rotation or angular velocity in xyz. So it is spent a little bit different from the transformation matrix. You may understand, okay? So for the Jn, if I have a Jn, if you are 6-axis robot, then you will have a 6x6 Jacobian matrix. So as I describe over here, it's a 6 by n in dimension because it depends on how many links you have. Yeah, and I would say links is not the very accurate item. Maybe how many joints you have. Yeah, some is revolute joint, some is a prismatic joint, but it's different. 买菜 Okay? Really okay? In my way, I try to put it another way to let you understand what is Jacobian. Yeah, of course, the textbook have a more, I would say, more comprehensive or more complete way for the derivation, but it's a little bit difficult to understand. Yeah, but in my point of view, if I expand by this way, it will be easier. And there are some basic rules I need to show you. Yeah, I did not copy that. Okay, should be here. Let me. Yeah. 哎，怎么了？哦，这里。Let me turn on my study over here, huh? Where did I see? Oh, here. Okay. 看有没有 Okay. Any jump, so it's a kind of difficult to explain. Okay. So remember we just explained for the J. For the J section, there is a turn you need to follow. Okay. So for the JV section, if you are the revolute joint I, then you need to provide one of the rotating axis for them. And rotating for what? The length. So the ON to the ON minus 1 is means from the joint to the other joint. Of course, you can put a different length. If you are interested in some point on the arm, then you put a length over here. So it's a linear velocity for the JV, for revolute joint. Later on, we have two practice cushion for you, so you need to understand about this. If it is a prismatic joint, it's okay. Yeah, because the prismatic joint is they move in the direction in Z direction. JB. For the J omega, is rotation velocity. So rotation velocity is easier. For the revolute joint, we just put the rotation joint vector, which is the origin, yeah, which is the link origin. But for the prismatic, is 0. Okay, let's go to the example. This is the very important one I want to show you. Okay, then you go to the example. Okay. Remember we just mentioned this. This is VJV part, right? JV part. It's a linear velocity section. For the JV part,是 JV 吗 ？O dot 对吧 ？O dot。Oh yeah, okay. For the JV part, we need to rotate with our axis. But for the prismatic, it just mentioned here. It's a ZI1. So you need to define the axis. Where is the axis vector? Where is the origin vector? Origin 它原点的向量是多少？这是 z i 减1。z i 减1。But how about the velocity? The velocity is a linear velocity because it is prismatic for this joint, di. So it come out the Jacobian item over there. They just only left zi minus 1 because it's prismatic joint over here. So I'm explaining this section. Prismatic. The JV matrix over there only left the origin vector. Let's continue another. So I always like to compare for you, okay? The same joint, but it's a revolute joint. The revolute joint for the linear velocity, still linear velocity. Okay, we are not go to the bottom one because the Jacobian have the linear velocity in the top, rotational velocity in the bottom. still a linear velocity. Linear velocity, you need to have one coordinate to let it rotate, right? One axis, let it rotate. So define what is the origin vector, zi, and the length from one origin to the next origin, or previous one, should be previous one. So this is O n, this is O n minus 1. Then you can put into the JV section for this joint. Yeah. So if you read through you follow my sequence, then it will be easier to understand because there are so many information in the textbook, I would say, but you need to organize a little bit. Over here, I compare the prismatic joint and the rotation revolute joint in only the JV section. What is JV section? Okay. Where's my JV section? JV section is linear velocity section. J omega section is the rotational section. To single one joint is 6 by 1. To n links is 6 by n. Rephrase again. So the upper 3 is for linear velocity. Maybe x, y, z. This is my assumption. Should be q1, q2, q3. For the bottom one is rotation. They describe the rotation quantity. So it's omega x, y, z. This is my define. Okay. So if you have n, you have one column for joint 1, one column for joint 2, one column for joint 6. This is the most important today. You need to understand this before you leave the classroom. Okay.